Good morning. Today we will tell about the theory of the closest packing. The difference in the variety of crystalline structures depends on the chemical nature of the substances, on the size of the atoms or ions, on the binding forces between them. The effective radius of an atom or ion is understood to be the radius of the sphere of its action, with the atom or ion being considered on an incompressible sphere. Atomic and ionic radius were determined experimentally by X-ray diffraction measurements of interatomic distances and calculated theoretically on the basis of quantum mechanical performance. A special table shows the atomic radius as the periodic table and ionic radius by Boki and Belov. They are the Russian scientists in chemistry. Under the symbol scrap element in every cell of the periodic table, written ionic radius in nanometers for the cases of different valency. We must remember that the atoms and the ionic radius don't match. Look at this table. For example, element titan. The atomic radius 0.146, ion charge 2 plus, and atomic radius 0.078. You can see the difference between the atomic radius and the ionic radius. Ionic radiuses obey the following laws. The first, within one vertical series of radio of ions with identical charge increases with increasing atomic number, since an increasing number of electron shells enhance the size of an atom. The second, for the same element, increases with the radius of the negative charge and decreases with increasing positive charge. A radius of the anion is greater than the radius of the action anion because there is an excess of electrons and the cation deficiency. The third, the size of atoms and ions follow the periodicity of the Mendeleev table or periodic table. Exception number element with number 57 to number 71 lanthanides, where the radius don't increase but decrease, and the family of elements with number 89 to 103 actinides are the same. In conclusion, we can say that the effective radius of the ion depends on atomic number and degree of ionization. Cn of the atom or ion is the number of the nearest neighbors of the same type of the atoms or ions in crystal structure. If the center of these atoms mentally connect with each other to straight lines in the general case, is obtained by a coordination polyhedron, Chi-M. Atom for which the polyhedron is constructed is located in the center. Coordination polyhedron doesn't require the external structure shape of the crystal and does not meet it. Look at these, please. The simplest coordination polyhedron are double, here, coordination number 2, triangle, coordination number 3, B, tetrahedron, coordination number 4, cube, coordination number 6. Why we must tell about the theory of the closed packing? In the early 20th century, a fairly large group of substances was discovered and the value of the interatomic distance is determined only by the presence of one type of atoms and totally dependent on the presence of the same structure of atoms of other varieties. This contradiction was explained by the theory of dense spherical packing or the theory of the closed packing. It is the same. The basic of this theory is the notion on the predominant role of atoms of one element in determining the structure. This type of atoms forming the frame of the crystal structure built of coordination polyhedron, which are atoms of other elements. Using the method of the closed ball packing reduces the difference between the most diverse structures to several factors: the order of the laws and the thinning factor of voids. Key provisions of the theory of dense spherical packing conclude in the following. The first, the densest ball packing is formed by parallel equidistant layers of equal-sized rigid balls densely adjacent to each other. And as here, called double layer or hexagonal, and alternative layers of type ABC, called three layer or cubic. You can see here. The gaps closed between equal-sized balls of two adjacent layers are called voids. What is the tetrahedral holes, as here, lie between the four related to each other isometric balls. The centers of these balls are the vertices of tetrahedron. Another voids or another gaps, octahedral voids, lies between the six balls, three closest balls here in the bottom, so that the hole of the upper layer is located just above the whole bottom layer. Tetrahedral and the octahedral voids can be completely or partially filled with atoms of other varieties. Proportion of filling voids ranges from 0 to 1. Ball arrangement itself occupies 74.01% of the volume. The remaining 25.95% of the volume can be used to fill the atoms of another species. In the tetrahedral voids can be increased ball radius of 0 to 22, where R is the radius of the balls constituting the packing. In the octahedral voids can be inscribed balls radius 0.41 R. By n balls, packaging mass octahedral n and 2n tetrahedral voids. The degree of filling tetrahedral site and octahedron is uniquely associated with the stoichiometric formula of chemical compound. Indeed, the connection I x by y c z, where the atoms A occupy tetrapause with a filling fraction of A, the B atoms occupy octopause with filling fraction beta, and the C atoms form a framework structure can be written as, you can see this form here. And on this statement are based the theory of close baking. And if you know the base statement of this theory, you can describe any crystalline structure and to analyze the stoichiometric formula of this substance. And our conclusion, look please the position pole in crystalline structure, octopause here and tetrapause here. You can see that tetrapause of course is less than octopause. And at the end of our lecture you can see the short video using by this reference. Thank you for your attention.